It's okay. I'll make do. Let me begin with a word of prayer. I will start here, guys. Heavenly Father, we thank you for this day, and I thank you for this class. Just ask you to bless our work today, Lord. In your name I pray, Lord Jesus. Amen. So, why is there an ant on me? It's not dead. They're never dead. All right, let's see here. So how do you solve L of y equals to f, where f is like something appearing in the homogeneous solution? So let's look at an example. Suppose you're going to solve y prime prime minus 3y prime plus 2y equals to, let's say, t. How would you solve this problem? So this is a non-homogeneous problem. We haven't solved these before. So here's the method. You go, well, I look at this. So I think if I make yp something like at plus b, that ought to do it. Now check it out. If I do that, yp prime is a, and yp prime prime, it's 0. So if I plug that in, take these, plug in, we get 0 minus 3 times a plus 2 times at plus b is equal to t. So this is the basic idea, is that you guess that the solution has a form that you'd expect based on differentiating the particular, the forcing function here. This is the forcing function. And the naive method basically says that you can just look at the forcing function, take a derivative of it, think about like what kind of functions appear, take a linear combination of those functions, plug it in, and then you can do what's called equate coefficients. And that will tell you, what the solutions should be here, the particular solution. So if I look at this from the constant term, I get what? I get minus 3a plus 2b. What's the constant term on the other side? What's the constant over here? What's the constant term over here? I'm waiting. T is not constant. There's no 1 over there. What are you guys seeing? Am I seeing it? I don't see a 1 there. Is there 1 here? 0, yes. All right. Now, the coefficient of t is 2a. What's the coefficient of t over here? 1. All right, now we got something. So this means a is 1/2, and b is what? 3a over 2, also known as 3/4. Right, so you put this all together, we get yp is 1/2 t plus 3/4. This thing I just did is known as the method of undetermined coefficients. Why is it called the method of undetermined coefficients? No, it's because these are undetermined coefficients at the start of the method, but actually maybe it should be called the method to determine the coefficients, which are at the beginning undetermined. But that would be a longer title, which no one would like. So that's just the particular solution. Remember, the theory says that the general solution is the sum of the homogeneous solution and the particular solution. What's the homogeneous solution here? We've got what? Lambda squared minus 3 lambda plus 2 equals to 0, which is lambda minus 1 times lambda minus 2 equal to 0. So thus, e to the t and e to the 2t are homogeneous solutions. And so consequently, the general solution has the following form. Y equals C1 e to the t plus C2 e to the 2t plus 1/2 t plus 3/4. And there you go. Solved. This is the general solution. What do you guys think? Too hard? I think, again, this is easier than what we started with, right? I mean, come on. It'll get worse. Example 2. Example 2. What if we're up against, I don't know, y prime prime plus 4y prime plus 5y equal to, I don't know, let's say e to the 3t plus cosine t. Can we solve this problem? All right. Let's see how it's done. So first of all, the homogeneous solution. I mean, you notice in my first example, I could have done the part in purple first. I could have done the part in blue and red first, right? They're not interacting, so you could do either one first. As a matter of habit, it's good to do the homogeneous part first. So note, we have lambda squared plus 4 lambda plus 5, which is lambda plus 2 squared plus 1. Therefore, lambda is minus 2 plus or minus I. Hence, y is equal to c1 e to the minus 2t plus cosine t plus c2 e to the minus 2t sine t. Not y, actually. This is the homogeneous solution. That's the homogeneous solution. All right, so let's stick a pin in that. We'll come back to it. All right. Your quadratic equation is useless here. Just saying, like what I just did is infinitely faster than solving the quadratic equation, muddling through. I've got complex solutions, blah, blah, blah. Like if you complete the square and you understand the pattern, you can directly read from here the root. That's what I just did. All right. So don't ignore that. Like notice that that's a technique that saves you time, and you're less likely to make an error if you understand what you're doing. All right, enough about that. The particular solution has what form? So this is the naive method, which means that it's not going to be right eventually. But if I take e to the 3t and I differentiate it, what do I get? E to the 3t, right? Yeah, so I just get other exponentials. Yeah? So for that, excuse me. Oh no, I can just do a e to the 3t. For the cosine, I've got a cosine, right? But if I differentiate cosine, I get a sine, so I got to throw in a c sine t. So this problem, I'm going to have 3 undetermined coefficients, a, b, c. And then what I usually do is I differentiate this thing. So I get 3a e to the 3t minus b sine t plus c cos t. And then I differentiate it again, which is 9a e to the 3t minus b sine t minus b cos t minus c sine t, right? So I form my particular solution, calculate its derivatives, and then I plug it in. Where do I plug it in? I plug it into the original differential equation, right? So I take these and plug into star. Star. All right, what happens? Well, we get ourselves a 9a e to the 3t minus b cos t minus c sine t. It's very important to distribute that 4 through. Plus 4 times 3a e to the 3t minus b sine t plus c cos t. and then plus 5 times a e to the 3t plus b cos t plus c sine t. All of that equal to the given forcing function, which was e to the 3t plus cos t. Then what I do is I determine the coefficients by equating coefficients once more. So I'm going to do the equating coefficients up here. I guess I can do it down here. Equate coefficients. So I've got my e to the 3t terms, I've got cosine t terms, and I've got sine t terms. These functions are linearly independent functions. All right? We could prove that, but I really don't want to. But trust me, they are linearly independent, and one of the quintessential features of a linearly independent set of vectors is that if you have an equation, you can equate coefficients of linearly independent pieces, the coefficients of those pieces. So like e to the 3t, I've got a 9a here. I've got a 4 times 3, which is plus 12a there. I've got a 5 times a there. And over here, I've got a 1 on the right-hand side. Therefore, 26a is equal to 1. A is equal to 1/26. Well, there we go. We're done. I would point out that the e to the 3t has essentially nothing to do with the cosine. Right? Like, these are two parallel stories that are happening at the same time, but they're not really interacting whatsoever, are they? If you look at the calculus here. How about cosine t? Well, I've got a minus b right there. I've got a 4 times minus b, so minus 4b there. I've got a 5 times b over here, so plus 5b there. And that's it for the left-hand side. For the right-hand side,
the minus will be a sign.
Oh no. So what should I do there? Thank you. Take that minus, make it a plus, and put a c there, right? Okay, good. This is, I was about to worry there's no algebra to do here. This is more exciting. So that's all equal to 1, and we can't really do anything more because we've got a b and a c in this story, right? Two unknowns, one equation. But good news, there's still the sine equation to look at, right? So here the sine equation gives us minus c, now minus my 4b, right, plus 5c equals to 0. All right, I'm going to do the algebra up at the top of the board over here. All right, so what we got is 4b plus 4c equals to 1. And we've got minus 4b plus 4c equals to 0. I see those equations, they just yell at me, add the equations. If I do that, I get 8c equals to 1. Therefore, c is 1/8. And if I know c is 1/8, then this equation right here says b equals c, right? So that's b. So we have now determined the undetermined coefficients, right? We found values for a, b, and c that make them work. And so let's put it all together. What we got? We've got y is equal to yh plus yp. This is like the general theory. Here, yh is c1 e to the minus 2t cos t plus c2 e to the minus 2t sine t. And then I've got plus 1/26 e to the 3t plus 1/8 cos t plus sine t, I think. It just so happened I could factor the 1/8 out there, right? So there you go. That's the general solution. This is I mean, this may be new to you, but I think once you understand what we just did, it should be like, oh, well, this isn't too hard, right? All we have to do is like look at the forcing function and just kind of like write down a linear combination of the things that can appear from differentiating it, right? And then plug it back in, work out the algebra, add the homogeneous solution. That's it. That's the general solution, right? So this seems too good to be true, doesn't it? Well, it is. Let me show you an example where this doesn't quite work. Example 3. Suppose we're up against y prime minus 3y equals e to the t plus, oh, I don't know, let's do sine of t this time. Oh, my bad. This will still work. I need to make that a 3. There we go. That's going to be a fly in our ointment. Rain on your wedding day, et cetera, et cetera. Let's see here. So first of all, what's the homogeneous solution? Here, the homogeneous solution is very boring. Lambda minus 3 equals to 0. So my homogeneous solution has the form C1 e to the 3t. Well, that was kind of anticlimactic relative to other things we've done, right? But there it is. That's the homogeneous solution. What would my particular solution be on the method that we've done so far, guys? Yp should be what? We do what? We do a e to the 3t for that guy, right? And then plus, it's the same as my last example, isn't it? So we'd have like plus b sine t plus c cos t, right? That'd be it. Same logic or lack thereof as the last example. I mean, we are just kind of guessing. But you know, if the guess works, then great. Yp prime is 3a e to the 3t plus b cos t minus c sine t, and that's all we need because this is a first order problem. I don't even need the second derivative, right? Plug it in. What do we get? Plug it in. What happens? Well, let's see here. So yp prime minus 3yp, in this case, is 3a e to the 3t plus b cos t minus c sine t. That's my yp prime. And then minus 3yp, so minus 3a e to the 3t minus 3b sine t minus 3c cos t. Right? All of that is equal to what? It's all equal to e to the 3t plus sine t, right? So if you look at this, we can make the sine t work out, right? So if you look at this piece here and this piece there, we can make that happen, right? We'd have what? We'd have b minus 3c equals to 0 and minus c minus 3b equal to 1, right? This is from cos t. This is from sine t. See that? And if I do the math here, that's what? I guess I would just multiply this by 3, minus 3. So that gives me like 3c plus 9b equals to minus 3. If I add these, I get, 10b equals to minus 3. So b is minus 3/10. And once I know that, c is equal to 1/3 b. So apparently that's minus 1/10. All right, great. So that part of the algebra works out. But when you have algebra like this, you can't just do that and ignore the other glaring like stick in your eye here, which is what? Can you see what the problem is? what happens? What do you got? You got here, this one, and you got this one. Those cancel, do they not? So if I look at e to the 3t and equate coefficients, I've got 0 equals to 1, which is not great, right? Like, that's not going to work, is it? And that's why I have prefaced this method that I've showed you today with the word naive, because it only works in as much as people shield you from deeper evils which surround you, namely the possibility that the forcing function and the homogeneous solution overlap.
All looks good to me.
All looks good to you. Well, hopefully that changes before the next test. Let's see here. So the issue here, what's causing this, the difference between this example and my first two is that the homogeneous solution has the same type as the forcing function. When there's this overlap like that, the naive solution won't work. At least not all of it. So to fix this, we need to introduce a method called the method of annihilators. Well, what's the method of annihilators? Well, let's look at that. So first of all, the method of annihilators simply reduces to the naive guess when there's no overlap. There's no overlap. Method of annihilators just tells you what you already know. But here's the method of annihilators. Suppose that there exists A such that A annihilates F. Then what happens if we operate on star by A? We'd have A times L y equals to AF, right? So to be clear here, guys, the annihilator and also the L, for the time being, I'm just thinking of both of these as being constant coefficient differential operators. So it's just a polynomial in the derivative operator, just like our examples today. This method does have an extension past that, but let's focus on the constant coefficient case to start with. So like what I'm saying here is that A and L, they're both polynomials in the differentiation operator. So like this is, you know, like some polynomial f of d. I better not use f, any other letter. Some polynomial g of d. And this one is some other polynomial p of d, right? And what happens when you multiply two polynomials in the differentiation operator? What do you get? You get another polynomial in the differentiation operator, right? But what is A of f? 0, right? So here's the deal. If this is like order, let's say, k, and let's say that L is an order n, you know, suppose this is, you know, let's suppose the degree of g is equal to n. So in other words, this is an nth order differential equation, and it just so happens that the forcing function can be annihilated by some order k differential operator. So like the degree of A is k. So my question to you is, what is this then? Isn't this just a homogeneous differential equation of order n plus k? What's its solution look like? we know what the solution looks like, right? It has the form y equals to c1 y1 plus c2 y2 plus da 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 plus cn yn plus cn plus 1 yn plus 1 plus da 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 plus c yn plus k yn plus k. And listen here, guys. The so like al y is also equal to LAY because these are polynomials, so they commute. So what that tells me, among other things, is that the homogeneous solution set to this problem, it must be contained in this general solution, right? Let me say that again. The solution to L of y equals to 0 is included in this. And that's not the part we're interested in, right? So for the sake of this discussion, let us suppose that this piece right here is YH. All right? So the method of annihilators simply points out that whatever's left has to be the form of the particular solution. So this right here is a blank, this is a template for the particular solution. Let me put this into practice for our example 3, show you how this works out. So for example 3, my f was e to the 3t plus sine t, right? So if I let a equal to what, I want a of f equals to 0. That tells me I should pick a equals to what? Which differential equation picks up e to the 3t plus sine t as a solution? I'm going to do it for you. So d minus 3 is what we need to kill off the exponential of 3t. That kills e to the 3t. What kills sine t? d squared plus 1 is what kills sine t. I'm working backwards like we were last class. I'm looking at sine t thinking, oh, that's a lambda equals plus or minus I kind of thing. That came from lambda squared plus 1, which comes from the differential operator d squared plus 1. And if I want both of them, I multiply. So there you go, that's the annihilator. So here, the L is just d minus 3 in this problem. So when I look at AL y, I just get d minus 3 times d squared plus 1 times d minus 3. Now I hope that you saw through my trap in your quiz and you realized that I gave you a problem where you had similar factors in different pieces of the polynomial. You can't ignore the commonality of that and write down the solution. You must combine factors to come to the logical conclusion. Now maybe you didn't do that on the quiz, but it's far better to learn that you're not doing that correctly on the quiz than on the test, right? That's why we have quizzes. I mean, I'd like for everybody to be right all the time, but I guess then I would never grade. Hey, wait, that's okay. I don't mind not grading. I hate grading. Anyway, so d minus 3 squared, d squared plus 1, right? And then I go back to last class. What's my general solution? My general solution would be like y equals c1 e to the 3t plus c2 t e to the 3t plus c3 cos t plus c4 sine t. Let me make that sine then cosine just for the sake of matching things up with what I've already done. It doesn't matter which order they're in, right? So you look at this, and what does that tell us? That tells us that, I mean, we have to do some interpretation here. This is the homogeneous solution, right? That's the homogeneous solution. So over here, this is the form of yp. All right? So my claim then is if we're looking at y prime minus 3y equal to e to the 3t plus sine t, we should make yp equal to a t e to the 3t plus b sine t plus c cos t. And my claim is also that we've already done the math for the sine and cosine part in what I already did on the board. So like that's going to go through the same. Like we could think of this, okay, fine, I'll just do the math again. Yp prime is, now we got product rule, right? You know, 1 plus 3t e to the 3t, factoring out the e to the 3t, and then plus b cos t minus c sine t. That's my yp prime. And if I look at yp prime minus 3yp, I get a times 1 plus 3 to the t, 3t e to the 3t, plus b cos t minus c sine t minus 3yp, which is so like the sine and cosine part of this algebra, it's going to go through exactly like we just did in example 3. So I'm just telling you the b and the c part of the algebra goes through just like we already did. All right. So, but the e to the 3t stuff is interesting now. So we can look at e to the 3t and we can look at t e to the 3t. Before, e to the 3t got us into trouble, right? Because that's where we got the 0 equals 1 equation. We don't like that. Now what happens? How many minutes do I have left? I got 10? All right, we're good. We're good. We're good. So, I mean, I can still talk after the video's done, I guess. I'll tell you what I think of the election. I'm a Calvinist. Anyway, sorry. You weren't expecting that. Let's see here. So this is I'm an idiot. A plus, wait a minute. Yeah, A, oh, there is no other e to the 3t, oh, so A equals 1. Well, that's kind of, all right, well, I guess A is 1, great. T e to the 3t, that's kind of more interesting. We get a 3a here from this term, right? But then we get minus 3a over here. How many t e to the 3t's over there? 0. So, yay. All right. And the math for B and C is same as before. And so what we get then is y is equal to C1 e to the 3t plus t e to the 3t minus 3/10 sine t minus 1/10 cosine t. There you go. Solved. That is the method of annihilators. It told us to multiply the naive part of the solution with the e to the 3t by t, but it also didn't tell us to multiply the sine and cosine piece by t. Yeah.
So between these two methods, we should be able to find all undetermined coefficients.
Ooh. Between these two methods, we can solve all problems. In context, yes. In order for this method to work, let's go back to the start and see when it works. This only works right? If L is a polynomial in the differentiation operator, in other words, it's a constant coefficient nth order problem. And what else? We also need that the forcing function appears in the same way. So the forcing function must also be a solution for some homogeneous problem. If neither one of those criteria are met, then further discussion's warranted. It turns out that this method has a generalization for a large class of differential equations. In fact, this method can be generalized to the Cauchy-Euler problem, which we haven't talked about yet. Cauchy-Euler problem, also known as equidimensional problem, is discussed towards the end of chapter 4. So if you guys are wondering where I am, I have both feet firmly planted in chapter 4 and also in chapter 6. The method of annihilators is covered in section 6.3 of the book, but it really justifies things which are just dropped from the sky in chapter 4. All right, so there's this grand, glorious, here's every single possible case known to man theorem that you can try to learn and memorize and or squeeze on your formula card or whatever. But I would strongly recommend that you learn the method of annihilators. In fact, I will test on it. So I do expect you to learn the method of annihilators. So in the interest of us getting good at the method of annihilators, let's just take the remaining, how many minutes do I have, Daniel? 6 minutes to write down some more annihilators. So let's try it out. So let's find the annihilator. We'll do more. I'm not done. We'll do more examples next class, all right? The algebra, for a given example, gets more troublesome than what we've done today, all right? But the methods we use continue to work. So find the annihilator. So given f, find lowest order A such that AF equals to a 0. All right. So here's choice of F, and here's the A I would use. So we'll start out with 1, t plus 2, t squared, e to the 7t, cosine of 2t, e to the minus 2t sine 3t, t squared cos t. Let's see here. T e to the 3t cosine of 6t plus t cubed. There, that's enough. I think if we understand these, we've done well. So you guys start me out. How do we get 1 as the solution to a differential equation? A equals what? T. Did I hear a D? I heard a D, right? I didn't hear a T. I heard a D, right?
Yeah.
OK, good. T plus 2. Just d squared will do. D squared annihilates this. Lambda equals to 0 twice has the solution set C1 plus T C2 T plus C2T. So 1 and T are the solution set to d squared, being the L, right? L of y, d squared y equals to 0. This is the logic, guys. D squared y equals to 0 gives me a lambda squared equals to 0, gives me y equals to C1 plus C2T, right? So I can see that T and 1 are in the solution set for that differential operator. That will kill 1 and T. And 2 is just 2 times 1. All right, T squared. D cubed, all right, very good. E to the 7t. D minus 7, we have a winner. Very good. Cosine 2t. So this is coming from lambda equals to plus or minus 2i, which means lambda squared plus 4 equals to 0, which is coming from a d squared plus 4 y equals to 0 differential equation. So working backwards, yes, d squared plus 4 is the annihilator you're looking for there. How about the next one? How much time do I got, Daniel? 2 minutes. All right, better give it to it. So here, no time for questions. D plus 2 squared plus 9. How do I know that? Because lambda plus 2 squared plus 9 has the solution set minus 2 plus or minus 3i. How do I know that? I know completing the square. You should learn it if you don't know it already. So lambda plus 2 quantity squared plus 9 equals to 0 is lambda equals to minus 2 plus or minus 3i, which is tantamount to writing this solution down by Euler's formula. You know the solution, but you need to really know it, right? You need to know it more intimately than you do perhaps already. T squared cosine t. This. What?
D minus 1 cubed.
Oh no. D squared plus 1. D squared plus 1 cubed. Because this is from lambda equals to plus or minus I thrice. That's where that would appear. And this one is a combination play. For the t e to the 3t, we need d minus 3 quantity squared plus 36. That picks up the you square that bad boy right there, square it, and then to get rid of the t to the cubed, you slap a d to the 4th on this guy. So what you told me, if I had t squared, Daniel, do I still have time? Dang it. Well, I guess that's it. Is it done? Did it stop? Yeah. Oh, but you guys are here. So